The topic is minimum cost spanning tree. So for that, first of all, we'll understand what does it mean by a spanning tree. Here I have an example graph. Graph is represented as G and VE. V is the set of vertices 1, 2, 3, 4, 5, 6, and E is the set of edges. The set of edges are from 1 to 2 and 2 to 3, 3 to 4, and so on. Graphs are represented as set of vertices and edges. Now what is this spanning tree? Spanning tree is a subgraph of a graph. Hence I should take the subset of this. So subset of what? Vertices and edges, both the subset or only one subset. So I should take the subset of edges. Vertices must be as it is. So I should take all vertices, 6. Spanning tree means I should take all vertices. Then how many edges? How many vertices I have? Number of vertices are n, that is 6. So I should take number of vertices minus 1, that is only 5 edges. Spanning tree is a subgraph of a graph having all vertices but only n minus 1 edges. So out of these edges, I should take only 5. So 1, 2, 3, 4, 5. I did not take this one. So this is a spanning tree. See, a tree will not have a cycle. So there is no cycle here. Yes. There is no cycle here. If this you can say it's a cycle. If you start from one vertex, you can again reach back to that vertex. But here, there is no cycle. Is it possible that I will take this one, but I will not take this? Yes, there is also a spanning tree. I will take this, but I will not take this. Yes, this is also a spanning tree. So which edge to select, that is a choice. That is a choice for a spanning tree. So I can say that S is a subgraph of a graph where S is defined as set of vertices and set of edges, where set of vertices are same as the vertices of a graph and edges are number of vertices minus 1. So the number of edges are number of vertices minus 1. This is how formally we can divide. In mathematics we can define like this. Now next thing, for a given graph, how many different spanning trees can be generated? I want to know that how many different spanning trees are possible. So see, number of edges are how many? 6. 1, 2, 3, 4, 5, 6. In a spanning tree I should take only 5. I should take only 5. So 6C5. Out of 6 edges, I have to select 5. How many ways I can do that? So 6 5C ways. So 6 5C is how much? 6 only. So I can have 6 different spanning trees. Just now you can see it is a simple one that I have skipped this edge. Like this I can leave one edge, right? And you can form a spanning tree, right? I can take all except this, take all except this, take all except this. 6 are possible. Suppose if I have one more edge now. Now I have 7 edges and I want to select 5. Now how many spanning trees are possible? See, I can have this spanning tree also. Or I can have this spanning tree also. Now possibilities are more. Now this is 7C5. 7C5. But this edge will form cycle. So how many cycles it is forming? This is one cycle and this is another cycle. So this edge is forming 2 cycles of number of vertices less than 6. So if it is forming number of vertices less than 6, then you will be 7C5 minus 2. So that's it. So what's the formula to know how many different spanning trees are possible from a given graph? So whatever the number of edges you have, you should take all those and see of how many edges you need. You need 5. So 5 is what? Number of vertices minus 1. So this is number of vertices minus 1 and minus number of cycles. You have to subtract number of cycles. I have a graph where the edges are having weights. So this is a weighted graph. This is a weighted graph. I want to know what are the possible spanning trees possible. So I'll draw a few spanning trees. Let us draw one spanning tree. This is vertex 1 and 2 and 3 and 4. So 4 vertices are there. Then how many edges I should take? 4 minus 1, only 3. So I'll select this one. 1, 2, 3. So what is the weight of this one? 5, 3 and 6. So what is the cost of this spanning tree? Cost of this spanning tree is 14. I'll take one more spanning tree. 1, 2, 3, 4. And I'll take these edges. Let us see what is the cost of this. 4, 6, 3. Then what is the cost of this one? 13. I'll take one more spanning tree. 1, 2, 3, 4. And I'll take these edges. This one and this one and this one. 4, 2 and 3. So this is cost is how much? 9. Now, from this example, some observation, we can understand something. If you have a weighted graph and you get different spanning trees, the cost of the spanning trees may be varying. You can get a different cost of spanning trees. Now, the problem is, can I find out the minimum cost spanning tree? Can I find out the minimum one which gives me minimum? Yes, you can find out. How? You can try all possible spanning trees. And then from that you can check whichever is minimum, you can pick up that answer. This is one method. Trying all possible spanning trees will be too lengthy. Is there any greedy method? Yes, the greedy methods are available for finding the minimum cost spanning tree. If a weighted graph is given, you can find out the minimum cost spanning tree by following the method without finding out all possible spanning trees. So what are those methods? One method is Prim's algorithm and the second method is Kruskals algorithm. There are two algorithms for finding minimum cost spanning tree. I have a weighted graph here and I have to find a minimum cost spanning tree by following Prim's algorithm. Let's see how Prim's algorithm works through an example. Now, as per Prim's algorithm, he says that from a graph, first of all, you select a minimum cost edge. So the smallest edge in the entire graph is this one. Then, this is the initial one. Now, for the rest of the procedure, always select a minimum cost edge from the graph, but make sure that it should be connected to already selected vertices. Now the next minimum is which one? 3 to 4. Don't take that. It will not be connected to 1 or 6. So take only those which are connected to 1 or 6. Means what he is trying to do is always maintain a tree. Prims thinks that if some farther away edge is selected, then it may not be forming a tree finally. So that is the reason he suggested that always select a minimum edge which should be connected. So let us see what is the next one. So for this connected one are this one and this one. So out of this 25 and 28, 25 is minimum. So select this 25. Then this 28 and 5 connected to 5 are 22 and 24. So out of this 28, 24 and 22. So from 1 and 6 and 5 I am checking. So already 6 is over. So 1 and 5. So out of those, this is smallest one. So 4 is selected. Now from 1, 6 and 5, 4, who is smallest? The connected one. So this is 24 and 18 and 12. So 12 is a smaller. So we will take 12. Then out of all these, which connected is the smallest? So here I have 24, 18 and 16. So 16 is a smaller. So take that 16. Then out of all these, who is next connected? So from 2 to 7 there is an edge which is connected. So this is 7. That's it. There are 7 vertices. So 1, 2, 3, 4, 5, 6. 6 edges are selected, and this is how we got a minimum cost spanning tree. And this is how we got a minimum cost spanning tree. What is the cost of a tree? The cost of a tree is, if I add all these, it is 99. So the approach of prims is initially select the smallest one, then always select the connected smallest one. Alright. So this is the method of prims algorithm. Next, if I have a graph 1, 2, 3, 4, 5, 6, 7. If I have a graph like this which is not connected, there are total 7 vertices, but there are 2 pieces in a graph. Can prim find out the minimum cost spanning tree for this one? No algorithm can find out, because we cannot find a tree for this one, spanning tree for this one. In a spanning tree, it must be connected. So for non-connected graph, we cannot find spanning trees at all. But if I start prims on this one, starting from vertex 1, if it is starting, then it may find the spanning tree for only one component, not the other component. Next method for finding minimum cost spanning tree is Kruskals method. This also follows a greedy approach. Instead of trying out all possible spanning trees, it shows a procedure by following which we can get a minimum cost spanning tree. It says that always select a minimum cost edge. Always select a minimum cost edge. Let us follow this one. Let's select smallest edge 1 to 6, that is 10. This one is the smallest, and the next smallest test is 3 to 4. So the second edge I am selecting is 3 to 4, and its cost is 12. Next minimum is 2 to 7. Select 2 to 7, and this is 14. And the next minimum is 2 to 3, that is 16. And after this, the next minimum edge is 7 to 4, but that is 18. If I select that, it will form a cycle. Yes, Kruskal method says that always select a minimum cost edge, but if it is forming a cycle, don't include it in the solution. Discard that edge, don't include an edge. So it means always select such that it is not forming a cycle. So if I include 4 to 7, it will form a cycle. So next one you check. So the next one is 22. So this is from 5 to 4 or 4 to 5. So this is 22. Next minimum is 24. So that is 7 and 5. If I include this also, it will form a cycle. Don't include that one. Then the next minimum one is 25. That is from 5 to 6. So this is 25. And the cost of this one is, if you add all these weights, it's 99. So here also I got the same result, just how I got in Prim's algorithm. So the Prim's algorithm and Kruskal algorithm has given the same result on this particular graph. Now time taken by Kruskal's algorithm, how much time it takes? See, it has to always select a minimum cost edge from the set of edges. So let us say there are E number of edges. So out of these edges, it will find out the minimum one. And how many such edges it will be selecting? It will be selecting V minus 1. Yeah, this number of vertices minus 1. So like we know in a spanning tree, if there are 7 vertices, we need 6 edges for forming a spanning tree. So that's 7 minus 1. So as many vertices we have, minus 1 number of edges we have to select. So the total time will be theta of V into E. There V is number of vertices and E is number of edges. So it is N into E. N is the number of vertices and E is the number of edges, which can also be written as N square. If we say both are N, then it is N square. So the time taken by Kruskal's algorithm is N square. But Kruskal algorithm can be improved. When we have to always select a minimum cost edge, then there is one data structure which will always give you minimum value. That is min heap. If min heap is used, then min heap will always give you a minimum value. Whenever you delete a value, you get a minimum value. So if all these edges are kept in a min heap, whenever you delete, you will be getting a next minimum edge. So you don't have to search. So from min heap, whenever you delete, the time taken is log n. So how much time it will take for finding a minimum cost edge? Log n time. So how many times you have to do that? That is n time, number of vertices minus 1 time, so n. So by using min heap, the time complexity of Kruskals algorithm will be n log n. So that's how Kruskal algorithm can be made faster. Now if there is a graph given that is not connected graph, it is having two components, 4 vertices on this side, 5 vertices on that side. Can we find a spanning tree on a non-connected graph? No, spanning tree is not possible. But what happens if I run a Kruskals algorithm? So Kruskal algorithm will try to find out total number of edges, that is 9 minus 1. So it will try to select 8 edges. And it will not be forming a spanning tree for entire graph, but it may be finding the spanning tree for each component. Let us say if the first minimum, the one it will select is this one, then the next minimum it is having more than one edges. Let us say it selects next minimum, and the next minimum it will select this, next minimum it selects this, and this is the next minimum. So in this way it is selecting the minimum edges from both the components, or it will be selecting from all the components. So it may be finding spanning trees for all the components, but not for the entire graph. So Kruskal algorithm may work for non-connected graphs also, but it may give spanning tree for those components. Let us take a problem here. A graph is given and the weights of the edges are also given, but here two edges are not having their weights. If I take only these edges which are having a weight, they are forming a spanning tree of a graph. Just hide these two edges, it becomes a spanning tree. Now the question is, what could be the minimum values of these two edges? What could be the minimum possible value? Maximum it can be anything, but at least what could be the value? See, as this is included in a spanning tree, this is included in a spanning tree, this is not included because it is forming a cycle. So it is forming a cycle. If it is included, this will form a cycle. So it may be considered after selecting these two. So the weight of this could be 4. Right? First this is selected, then this is selected, then this is not selected, means definitely it is 4. If it is less than 4, then that would have been selected first. Right? So it came later, so it is forming a cycle, so it is not taken. Then this 4 is taken, then this 4 is taken, this 5 is taken. So then what could be the minimum weight of this one? So it is not selected, at last it is left over, means minimum weight of this one could be 6. So this is 4 and that is 6. So if any missing edges are there, you can find out. This type of problems we find in examinations. So some missing edges you can find out. So if you know spanning tree, you can answer this type of question. Let us take this example and let us find out spanning tree for this one. Minimum cost spanning tree. So if I follow Kruskal's method, so first I will select the minimum cost edge. This edge I have selected. Then the next minimum is this 3 and that 3. So I can select any one. So I will select this one first. This is selected. Next I'll select this one. So is it forming a cycle inclusion of this one? No. So I'll select that one. Then which are the edges? 4 and 4. These two are there. So I can select any one. So I'll select this one. Whether this will form any cycle? No. So total how many edges I have selected? 1, 2, 3, 4. And total how many vertices are there? 5 vertices are there. So 4 edges are selected. That's how I got a spanning tree. So what is the cost of the spanning tree? 2 plus 3 plus 3 plus 4. And this is 12. Spanning tree is a minimization result. So definitely there will be only one result. So for a problem there can be only one optimal solution. So we should have exactly one spanning tree only. There cannot be more than one spanning tree. Right? But in this example you can see, instead of taking this 4, this edge, I can take this 4 also. Now also it's forming a spanning tree. Yes. So I can select one more. But what is the cost? Cost is 12. So cost is only 1. the optimal cost is 12 only, you will get definitely only one answer in the minimization or maximization problem. But for that answer, the set of input may be changing. So either you can include this 4 or this 4. So total how many spanning trees are possible? 2 spanning trees are possible. But what is the minimum cost? That is 12.